Okay, we're going to rig the next speaker, who is Marc Juarez from KU Leuven, and aptly he's going to talk to us about website fingerprinting defenses at the application layer. Thank you.
Thank you. So, good morning, everyone. I'm going to present the joint work with Giovanni Cherubin, who you already know from Royal Holloway, Jamie Hayes from UCL, and myself. And this is work on defenses against website fingerprinting. So, as Giovanni already explained, website fingerprinting is an attack that allows an adversary that is sitting between the user and the entry card and looking at this traffic to identify the pages that users are browsing through Tor, even though the traffic has been encrypted and anonymized by Tor. And the main intuition behind the attack is that pages are very different to each other, so they have different images, different text, and all these differences can be observed in the traffic. And this is the side channel that the attacker exploits. So, So in particular, in this paper, we focus on hidden services. These are websites that can only be accessed through Tor. And users can visit them without having to resolve the domain name to an IP, which makes them very suitable to host sensitive content because they cannot be located geographically, or it's very hard. Here we see some examples of hidden services. I won't get into much detail on how the protocol works, but you need to know that it's very different with respect to the protocol that Tor uses to browse regular sites. So normally, Tor builds 3-hop circuits, and actually for hidden services, they are 6-hop, but there are other differences. And in 2015, a paper by Kwon and others shown that these differences can also be observed in the traffic and can be used to distinguish visits to regular sites from hidden services. So this is very threatening for website fingerprinting in hidden services because an adversary that wants to fingerprint a hidden service can filter out all the visits to the other sites. And then the world becomes much smaller. There are many fewer hidden services, and they are thus potentially more identifiable. And on top of that, they are, as I already said, they are more likely to host sensitive content. And this means that users that visit these hidden services may face more serious consequences if the attack is successful. So that's why we decided to focus on hidden services. So defenses, how do we protect against this attack? So there have been already some defenses that have been proposed in the literature. You can see some of the names on the slide. And the main primitive they use to defend is to generate dummy packets, fake packets, or messages that are mixed with real traffic to perturb the features that the attacker exploits. And for this to be effective, the dummy messages have to be indistinguishable from real messages, and the padding should run at least 1 hop further than what the adversary can see. And these defenses were theoretical, and they were designed in the network layer. So these messages, the fake messages, are actually TCP packets. And for this reason, they require control over how TCP generates these packets and the timing of these packets, which is very difficult to implement in practice. So this brings me to the key point of the paper, which is that we propose to design the defenses at the application layer. We argue that it's as effective as doing it at the network layer, because if you can conceal the features at the application layer, which is where the identifying information of the page is found, then the patterns will follow down the stack, and they will still be concealed also at the network layer. So if you think about it, if you have 2 identical pages at the application layer, they have the same images, the same content, they should be also indistinguishable at the network layer, right? And this has some advantages. So the main advantage is that they are much easier to deploy, the application layer defenses. You don't depend on Tor to implement them. They build on top of Tor. And also come with some disadvantages. For example, the padding has to run end-to-end, as opposed to network layer defenses where the padding was dropped at the entry or the middle. And depending on how they are designed, they may require server collaboration. But this is not a problem for us, because since we are taking the case of hidden services, we assume that hidden services are interested in providing privacy to their visitors, so they probably have incentives to support these defenses. So let me introduce you to the two defenses that we have developed and evaluated to explore the space of application layer defenses. So the first one is Llama. It's a client-side defense implemented as a Firefox add-on for the Tor browser. It applies on, so the operation is on the HTTP requests, and it adds more delay. It's focused on adding delays. And as you see, this is what I meant by they don't depend on Tor, because a user that wants to get the benefits of this defense can just install the add-on on the Tor browser, and that's all. Then Alpaca is a server-side defense. It's actually the first server-side defense that has been developed and evaluated against website fingerprinting. And it's applied on the actual files in the server. So we implemented this as a script that will crawl the files in the server and apply the padding on these files. And again, like the service operator can just run the script, doesn't depend on Tor. And just to clarify, this is not a client-server solution. These are two independent solutions that can run standalone. And this is how we evaluated them. So I will explain Alpaca first. Alpaca defines the page as a set of objects. So the only important features, since the contents are encrypted, the only important features are the number of objects and the sizes of these objects. And the protection strategy is to give an original page and a target page. It will pad the objects in the original page to match the objects in size and number of objects in the target page. So we didn't want to impact user experience. We wanted the pages to, the user not to see any difference in the page when it's presented to him. So we came up with some tricks to do that. So for example, we added the padding as random strings in the comments as comments in the HTML of the page. Or we added the random strings in the metadata of the images. And also, if we had fake objects, we would use the hidden CSS style in the HTML. So the padding is still sent over the wire, but the user doesn't notice. So how to define this target page? So there are two ways this can be done. So first, when this target page exists. So in this case, if you want to protect secure drop, and you want to, and the target page is Facebook, you would Alpaca would arrange the objects in secure drop so that it adds the optimal padding to make these objects look like some other objects in Facebook. Then the other strategy is the other strategy is to create a collision. So two pages that are slightly similar, we add the right padding in each one to create a collision, and the classifier would confuse them. For that, there are two ways of doing this. So one is based on two parameters that define the padding. So we pad the objects to the next multiple of these parameters. So for example, here, if SecureDrop has 2 objects and Facebook has 3 objects, then, and the parameter is 5, let's say, or 4 in the example, then you would add as many objects as to reach 4 objects. So this creates like an anonymity set of the pages, and these pages will collude. The other way is probabilistic. We crawled the hidden service space, and we estimated the empirical distributions of number of objects and the sizes of these objects. And what we do is, when we protect the page, we sample from this distribution randomly. So the other defense is Llama. It's inspired by randomized pipelining. Its goal is to randomize the HTTP requests. And we do it by adding some random delays in the HTTP requests. And then we repeat also previous requests to generate padding responses. It's more of an experiment to test randomized pipelining, because randomized pipelining was shown to fail in several evaluations. And we want to see if it was because of the way it was implemented. So we implemented it as an add-on, and we don't require server collaboration. So the evaluation is very simple. The methodology is very simple. We just cached 100 hidden services in our own hidden service that we were running. And we visited these pages with and without the defense. And we then measured security by applying the state-of-the-art attacks on the unprotected and the protected case. And then we compared the accuracies that we got. We measured performance by measuring the latency and the bandwidth overheads after applying the defense. So I will just give a highlight of the results of the evaluation. So here you see the results for Alpaca. We tested several configurations, but I'm only showing the best one. So in this case, in the left side, you can see the blue bar is the unprotected case. So one thing to notice here is that actually the accuracy in the protected case is very small compared to, it's quite smaller than the accuracies that typically website fingerprinting attacks achieve on regular sites. And we believe this is because hidden services are very small, and they are very similar to each other, and they are more likely to collude in some of the features, actually in the length features. So we see that in the best case, best case for the defense, when we apply the probabilistic Alpaca, the accuracy of the attack decreases to 15%. And the bandwidth, so the decrease in accuracy ranges between 60 and 40% for all the configurations. And the bandwidth overheads are, for the probabilistic, are 50% latency and 85% bandwidth overheads. And these numbers are in the range of the values that network-level defenses achieved. Llama, on the other hand, didn't seem to provide as good a level of protection as Alpaca. We see that the accuracy only decreased around 20 and 30%. And although the latency and bandwidth overheads were very low, it's a very lightweight defense, but probably it's not enough. And we believe this is because randomizing the requests is very hard because there are some dependencies on the content that is requested. So this limits how much we can randomize. And this is probably the same reason why randomized pipelining is failing. But we haven't tested how much randomization do we have. So the main takeaways are that website fingerprinting defenses are easier to implement and deploy at the application layer, and they are as effective as in the network layer. We have shown that hidden services have incentives to support these defenses. And we have developed the first server-side defense in Tor. And actually, we were contacted by SecureDrop, a whistleblowing platform that runs the hidden services, and has been implemented a prototype of Alpaca that will eventually be deployed. And Alpaca is also running in this hidden service if you want to visit for a demo. And the source code is available on GitHub if you want to play with it. So yeah, that's all. Thank you.
Yes, thank you, speaker.